Assalamu alaikum students. On behalf of the Department of the Electrical and Computer Engineering, Comsets University Islamabad, I, Ali Roman, welcomes you all to our online learning session for the course Digital Logic Design. This session will be our first session regarding combinational logic, and we will be learning some basic concepts regarding design and implementation of combinational logic circuits. So before formally starting our session, let us first review what we have studied so far in our regular sessions. We have learned that how to deal with digital systems, as a digital system can be described by a Boolean function or a truth table or a timing diagram, and last but not the least, logic diagrams or detailed block diagrams. We have learned about logic gates and the basic concepts regarding Boolean algebra, as well as the gate level minimization techniques such as K-maps. So I hope so you all remember those concepts in our class sessions which we have studied. So to start with, let us see the contents which we will be describing today in our today's session. So students, first of all, we're going to define what are the combinational logic designs and circuits are with a brief introduction about those sorts of circuits. Then we're going to discuss the design procedure which we use to opt while implementing the combinational logic circuits. And normally all our digital circuits can be categorized into two categories. Either the circuits can be combinational or the circuits can be the sequential circuits. So our emphasis today in this session will be on the combinational logic design. So we'll start with the two design examples. The first one is the code converter, in which we will gonna learn about how to convert a BCD code, that is the binary coded decimal system. The system or the converter used to accept a BCD number as at its input and gonna convert it into the access tree code. So we're gonna follow all the design procedures which are required to convert the BCD number into the access tree code. Then we'll switch to the basic adder circuits. Adders are the basic components which are used in the digital circuits and are frequently used. We're going to study about the half adder. That is a circuit which has the capability to add two binary bits. Then we're going to switch to the full adder circuits. We can say that after studying the half adder circuit, the circuit that only has the capability to add two binary bits. But for the full adder circuit that has the capability to add three binary bits, we're going to discuss that in detail. After studying half adder and full adder, we're going to switch to the binary adders, which is going to utilize the full adder circuits. So binary adder circuit will be a circuit that has the capability to add multiple binary bits. So these are the contents which we're going to discuss in today's class. As far as the reference readings and the acknowledgements are concerned, we're going to follow our course book, that is the digital design, with introduction to the Verilog HDL, and we're going to follow chapter number 4. So to start with, I just want to mention that all the snapshots and figures and tables are taken from the same chapter. So please consider page 144 till page 157 after completion of this session for your reference readings. So students, to start with our discussion, the combinational logic circuits, let's first describe what are the combinational logic circuits are. So in this slide, we're going to present the basic concepts that are related to the combinational logic circuits. So to describe a combinational logic circuit, how we're going to identify that it's a combinational logic circuit or something else. A combinational logic circuit is a circuit that is just the interconnection of logic gates. Well, a simple and straightforward a circuit that is a connection of interconnection of logic gates that has some set of inputs and that has some set of outputs, and output is only and only dependent upon the applied inputs at any time instant. No prior history is required, no feedback elements are required, no memory elements are required. So the simple and straightforward circuit, we're going to apply some inputs, and at the same time instant that input is being processed in a specified way and the outputs are generated depending upon what are the designs of the combinational logic that are being implemented and in that specific block. So if you see at the figure, that is figure 4.1, that describes the block diagram of the combinational logic circuit that has a set of inputs. The n are the number of inputs. In this box that has been described as a combinational circuit that have some sort of description, circuit description, which is going to describe how the outputs, these are the set of outputs, are related to the inputs. So at any time instead, we're going to apply the inputs and the outputs are generated. The same thing which you are following in your lab sessions, in which you're going to use the 74 series ICs and you're going to connect your ICs on a breadboard and you apply input from the switches and the outputs are generated and you observe the outputs on the LED. So those sorts of circuit are basically the combinational circuits. So till now, whatsoever we are studying were the basic concepts regarding the combinational logic circuits, and the sequential logic circuits will be discussed later in the later sessions. So uh, simple, straightforward. These are the circuits that has the interconnection of logic gates in which outputs are only and only dependent upon the inputs at any time instant, and circuit don't have any sort of memory element or the feedback mechanism. As far as the example of feedback mechanism or the memory elements are concerned, in a computer system contains both sorts of circuit that can be combinational and that are the sequential circuits. The memory elements, the RAM that has been installed in your computer system, or any sort of memory element that has been used by your computer system, that is basically a sequential circuit. That do possess memory elements and that do have some feedback mechanism. For example, the latches or the flip-flops that are being used in your in the computer system, that are basically the pure sequential circuits. So we're going to discuss those stuff later, but today we're going to focus totally on our combinational logic circuits. So the combinational logic circuit, we can imagine it's a block that receives some sort of inputs at any time instant, and we're going to produce the output, and the circuit going to process that depending upon the Boolean function, or the you can say that uh, whatsoever the description of the circuit is in order to describe that particular circuit. So coming to the next slide, so the important thing is what are the design steps or the procedure which we will follow in order to design the combinational logic circuit. And the very interesting thing is that we are normally following those design procedures or the steps while designing the basic modules in the digital circuit till now in your lab sessions as well as your courses as well. The first important thing is that for any circuit, for any given specification, the most important thing is to determine the ports. While I'm discussing about the ports are the basically the interconnection which are used to provide the inputs and outputs to the system. So what are the basic inputs of the system and how these inputs should be processed and what are the outputs. So the first step is to identify the inputs and the outputs. Once we have identified the inputs and outputs, we have labeled the inputs and outputs with some specific and unique names. The next thing is to describe the relationship between the inputs and outputs. Now the relationship can be described in several ways. Either we can have a timing diagram in order to describe the relationship. Either we can have a truth table that is a table basically that used to present all the possible combination of inputs and outputs. Or we can have a logic diagram that basically represents the interconnection, how the inputs are being processed by the circuit in order to generate the outputs. So the second step is to drive the truth table. We can say among these three steps, the basic step is to drive the truth table, defining the relationship between the inputs and outputs. And the third step is to obtain the simplified Boolean function if they require if it is required for implementation. Now the simplified Boolean function, why it is important? Because uh, as a designer's point of view or as a scientist point of view, because I'm referring by computer science students as a scientist. So the most important thing is that how we're going to implement that system that is cost efficient, that is the resource efficient, resource in terms of area utilization, uh, uh, performance, you can say, and that has the least power dissipation. So those sorts of circuit require the minimum number of resources. So in order to implement a system that do possess some minimum number of resources, we have to simplify our Boolean functions by using the circuit simplification techniques, which we have already studied in our sessional 1 portion. So once we obtain the simplified Boolean function, and then the next step is to construct the logic diagram and verify the correctness of the design. Now the most important thing is that how we're going to verify the correctness of the design. So there are several ways to verify the correctness of the design. Either the correctness of the design can be verified from the simulations. We have some simulation softwares in which we're going to implement that stuff and we're going to verify, and those sorts of simulations are known to be the functional simulations that are used to verify the functionality of the design. Or we can dry run the system and manually provide the inputs. and check the behavior of the outputs regarding those inputs. Or the third step is to construct the circuit physically and to verify the functionality by providing the inputs and verifying the inputs and outputs through the truth table. So these are the four basic steps, and the most important thing is that these are the steps which we were following in our session 1 portion while describing the basic modules that are related to the digital logic design. So I think so these steps are very much obvious and clear. So these are the steps which we're going to follow while designing any sort of combinational circuit in detail. In the later sessions, we will be discussing some specific examples that are used to implement the combinational logic designs. For examples, adders, the subtractors, encoders, decoders, multiplexers, demultiplexers. So these are the basic building blocks for any digital design and that are frequent use while designing any sort of combinational logic circuits. So coming to the next slide, which we have discussed while describing the content, that we're going to follow the two design examples. The first design examples covers a code converter. So the code converter which we have selected is the BCD to XS3 code converter. So let us first discuss what is the BCD to XS3 code conversion mechanism. So how we're going to implement that circuit. The most important thing, just remember those design procedure and the steps. The first thing is to identify what are the inputs and what are the outputs. So this is the block or the converter circuit that receives the BCD number at its input. So BCD stands for the binary coded decimal. So each decimal digit is being described as a 4-bit binary code. So this system will going to receive a BCD number at its code. So we've got the 4 distinct lines that will carry the BCD information to the system and convert it to the XS3 code. So XS3 code is also a 4-bit code, and from this specification, it is clear that the inputs of the system are 4-bit that are going to receive a BCD number at its input, and the output is the XS3 code. So XS3 code uh, is also 4-bit code. So now, what is the XS3 code? How the system will gonna convert that input into the output, and what sort of mechanism is applied while the conversion of the BCD code into the XS3 code. So as far as the definition of XS3 code and the relationship of the XS3 code with the BCD code is that XS3 code, whatsoever the XS3 code is, that is always 3 greater than the applied BCD code. At any time instant whatsoever the BCD number is applied from 0 till 9, a 4-bit binary code. So the output code is always 3 greater than the input code. So the step 1 which we've discussed, that to determine the inputs and outputs. Here you can see a block diagram in which we can see that the A, B, C and D are the literals that are going to represent our inputs. So these are the literals that are basically representing a 4-bit BCD number, whereas the definition of W, X, Y and Z are the 4 output lines containing the XS3 code. So this block is going to convert the BCD code, going to receive the inputs at A, B, C, D, process those inputs, and going to convert the output to the W, X, Y, Z, and this is the resultant, which is basically the XS3 code. So this was the first step in which we had identified what are the inputs and what are the outputs. And the next step is how these inputs and outputs are related to each other. That is basically to drive a truth table. So as far as the description of our design tasks, I have already mentioned that the XS3 codes are always 3 greater than in magnitude than the applied inputs. So table 4.2 basically specifies the relationship between the inputs and outputs. Here you can see that A, B, C and D are the inputs that are carrying a BCD number, and the outputs are labeled as W, X, W, X, Y and Z. These are the outputs. The important thing in this table is that D is being considered as the least significant bit and A is being considered as the most significant bit as far as the order of the code is concerned. Similarly, for the output, Z is considered as the least significant bit and W is considered as the most significant bit. Now, let's see the table how these conversions are done. If we see that if we applied the input A equals to 0, B equals to 0, C equals to 0, D equals to 0. This is the BCD code for the decimal digit 0. So as I already have mentioned that the output is always 3 greater than the input. So 0 plus 3 equals 3. So the XS3 code for uh, this combination is w is equal to 0, x equals to 0, y equals to 1, and z equals to 1. Let me see if I've got some other options. So if we see this combination, so the output is 3 greater than the input. The input magnitude was 0 and the output is 3. So the accessory code for the BCD number 0000 is 0011. Similarly, for the combination that is 1001, that is basically the BCD code for the digit 9. So the output code should be 3 greater than the input. So if you look at the table, that is W is equal to 1, X equals to 1, Y equals to 0, Z equals to 0, which is basically the binary code for 12. So the output is always 3 greater than the input. Now the important thing is that since the input is a 4-bit combination, so we've got the maximum combination of 16. What happens to the rest of the combination that are greater than 9? Are they a valid BCD number or not, which we have already discussed while adding the BCD numbers in our previous sessions. So for that cases, if those are the cases that are applied at the input, what would be the status of the output then? Since that are not a valid BCD number, the output should be undefined in all those possible combinations. For example, the combinations from 1010, that is the binary value of 10, and 1111, that is the binary value of 15. So from 1010 till 1111, these are not a valid BCD numbers. So the output should remain at its undefined state. So W should possess a value of X. X has been labeled as an undefined state. uh, X should possess a value of X, that is an undefined state. Y should also possess the value of X, that is also the undefined state. And Z should also possess the value of X, that is also the undefined state. As far as the undefined states are concerned, undefined at any time instant, the variable can possess either 0 or 1 depending upon what are the cases that are most beneficial. So we can treat X as a 0, we can also treat X as a 1. So to start with our first task from the given table, what you have to do is to find the Boolean functions for W, X, Y, and Z in canonical and standard forms of expression, which we have already discussed in a session 1 portion. How we're going to convert that? We're going to see, for example, for the W, we're going to see what are the instances at the output that do possess a value of 1. For example, these are the instances that do possess a value of 1. At that specific time instant, we're going to see the inputs, and we're going to represent those inputs in the min terms of the maximum formats, and we're going to add them or multiply them depending upon the form of expression we are converting. So this is the thing which you're going to perform for the task 1, that also carries the revision process for how representing an expression in a canonical or standard form, and how we're going to extract that expression by using the truth table. So to start with, from where we've started from the point in which we defined our inputs and outputs. We've labeled those inputs and outputs. We identified the requirements of the circuit. Either we are having the inputs of 4 bits and the outputs are also for the 4 bits. Then the next thing is to relate that inputs and outputs, in which we are going to follow the table 4.2, which is presenting the relationship between the inputs and outputs, and that is basically the second step that is driving the truth table. Now coming to the third step, once you've achieved the Boolean functions either in a canonical or standard form, the next step is to implement those Boolean functions either in their base forms, or we can simplify those Boolean functions in order to optimize our resources. So as we have discussed earlier, that we can implement the Boolean expression obtained from the truth table in their base forms, but their implementation will result in more resource utilization. hence increasing the circuit cost. More number of resources, because the cost is directly resource related to the number of resources. More number of discrete components, and those components do possess some cost cost. So bigger the circuit is, more number of resources are, more costly the circuit is. And similarly, for the power and area utilization for the circuit, implementation will also increase. So to avoid that, to implement the circuit in the best optimal way, we use those sort of techniques which are used to simplify our expression for the optimal implementation. So let us see the figure 4.3 that do involve some sort of optimization or simplification techniques which we have studied already in our session. So that is a simplification technique. Basically, if we see that we are using K maps for that, figure 4.3 presents the maps for the output Z, Y, X, and W. Z, Y, X, and W. Since the inputs are 4 bits, so we're going to construct a map of 4 literals here. Uh, if you see the map in detail, that the combinations starting from 1010 till 1111. These are the combinations starting from 1010. This is 1010. This is 1010, 1011, 1100, 1101, 1111, and 1110 possess the value of x. So here the pairing depicts that we've considered the x as 1 because we are making the pairs depending upon the min terms. So if we see the pairs that have been constructed here while representing the expression for the z, relationship for the z, it's a pair of 8 blocks or the 8 cells, and the term which is not changing within those pair in all the 8 cell is basically the d in its complemented form. If we see the d here, its value is 0 for all these 4 pairs, and similarly it's same here 0 for all these 4 pairs. So z is being represented as d prime. Similarly for the y, if we see that we've got 2 distinct pairs. The first pair is this one, and the second pair is of 4 cell is this one. If we see the first term that is being extracted from this pair is C into D, C and D. This is the term C and D, because C and D are the terms, are the literals that are not changing within a cell, within a pair, while rest of the inputs A and B are basically constantly changing within the pair. And for the rest of the pair, the second pair, we have extracted C prime, D prime. So the sum of product expression is C into D, C and D, or C prime and D prime. Similarly, the rest of expression for the X and W are being represented here in these maps. So these are the simplified expressions which we have attained from these maps, and we can see that these expressions are being converted into its equivalent form in order to optimize some resources. For example, this C or D term is mostly common between all the outputs. So instead of implementing this thing every time again and again, we're going to implement one OR gate that going to process C or D, and whatsoever the connections are with the remaining outputs, we're going to provide those connections. So these are the simplified expressions. I hope so from this process you got the same sort of expressions. The second task which I've designed for you is, the first thing is that there is a small minute mistake in the maps. Uh, can you identify that? From where the value of x came from and why? So this is the important thing, because every map do possess some values that are undefined. Why these undefined values are being placed in the map, and what is the benefit of placing those undefined values in the map. So these are the things which you're gonna discuss while we'll having some online sessions. Now coming to the final step, to start with, from where we have started, we have defined the inputs and outputs. The second thing was to drive a truth table to define the relationship between the inputs and outputs. The third step was to simplify those expressions obtained from those truth table, and the fourth step is to implement those in terms of logic diagram and verify our results. So this is the detailed logic diagram that is being represented in figure 4.4 regarding the expressions which we have achieved in our previous slide. So if you see z was equal to d prime, if you see the expression z was equal to d prime, so this is the d input that is being inverted here in order to produce z. Similarly, if you see the expression, we have got c or d, so that is being common between y, x and w. And if you see the diagram, this is the gate that is basically gonna OR the input C and D. So wherever C or D is required, these are the lines that are being provided, and wherever C or D prime is required, this is the line that is going to provide C or D prime to Y to X. So this is the logic diagram. How we're going to verify this logic diagram? At any time instant, just place the value of A, B, C and D. Process this diagram to generate the output W, X, Y and Z. If these outputs are generated the same as represented in the truth table, then this logic diagram is functioning correctly. And if there is a contradiction in that, then I think so this is the point in which we're going to identify that either we have created or we have conducted any sort of mistake in all this process, or we have not correctly implemented the logic diagram. So these are the four steps. I hope so these four steps are now cleared while discussing the design example 1, in which we've converted a BCD code to the access tree code, starting from the scratch, defining the relationship between the inputs and outputs. First of all, labeling the inputs and outputs, then defining the relationship, then simplification, then implementation and verification. So these are the steps which we're going to follow while discussing all the rest of the combinational logic examples. Now coming to our second design example, that is the implementation of basic adders in our computer systems. Basically, computer systems used to perform variety of information processing tasks, and those information processing tasks do utilize some arithmetic operations. While the arithmetic operations are concerned, that are the basic operations that are related to the addition, subtraction, multiplication and division, that are frequently carried out while performing any sort of you can say information processing task. So the most basic operation is basically the addition of two binary digits. When I'm saying that the two binary digits, you can say that two binary bits also, while bits is being defined as in terms of storage. So if we're gonna add 0 to 0, the result should be 0. Here the important thing is that this plus operation does not represent OR operation. It represents the basic arithmetic operation, that is the addition operation. So there is a difference between the OR operation, that is the binary operation, and this addition, that is the arithmetic addition or the basic addition. So if 0 is being added to the 0, the result is 0. 0 is being added to 1, the result is 1. 1 is being added to 0, the result is 1. And the important thing is that when both the digits are 1 and 1, so the result is basically 1 plus 1 equals 2, that is the 1 0, where 1 is being considered as the carry bit and 0 is being treated as the sum bit. So starting with the half adder, half adders are the circuit that has the capability of adding two binary bits or the two binary digits. So these are the circuits that has the capability to add two binary bits. So the inputs here in this block diagram are X and Y. These are the two binary bits that are being added, and the resultant are sum S to represent the sum operation, and C, if any sort of carry is being generated, that is being presented with C or represented by C. The input variables designate the occurrent and addend bits. The output variables produce the sum and carry, which I have already discussed. So consider X and Y, basically that are the two binary input lines, and S is represented for sum and C is represented for carry are the outputs. So these are represented in this block diagram. X and Y are basically your inputs, and S and C are basically the outputs of the system. Now coming to the second step, that is the truth table. Uh, that has been represented in table 4.3. If 0 is added with 0, we've got sum 0 and no carry is produced, so C is also 0. If 0 is been added with 1, the sum is 1, the carry is 0. The important case, that is the different case, that is if 1 is being added with 1, in that case the sum is 0 and a carry is being produced at the output. So we can represent these sum and carry into the Boolean functions. We can say that sum is basically equal to X prime into Y, or X into Y prime. These are the two main terms that are being associated with sum, in which we've got the instance that is equal to 1, and we're going to carry out we're going to get those combination of inputs and represent those in terms of min terms format. Similarly, for the carry output, if we see that this is the instance in which the carry output is 1 and the inputs are X equals to 1 and Y equals to 1, which are being represented as X into Y. So the next step is the logic diagram. The final step is if we see that figure 4.5, that has the two implementations for the half adder circuit. Basically we have implemented those Boolean functions. Here X and Y prime are applied on this AND gate, and X prime and Y are applied at this AND gate. Basically each min term represents the AND operation. So the number of min terms represents the number of AND gates in the logic diagram, and the output of these AND gates are then all to produce sum, and similarly the carry output. Similarly, if you observe the pattern here in the Boolean expression, that is X and Y prime, or X prime and Y. This is basically the expression for the exclusive OR gate. So we can replace this diagram with an exclusive OR gate. So both of these circuits are same. One is utilizing the exclusive OR gate and the others are utilizing the primary gates that are AND or NOT. I think so this is now clear. Now we'll move a step further because if in case of any addition there is a case that we have to add a carry in that. Let me see if I can quote some example here regarding the decimal number. Um, Let us consider the first number as a 457, 457. The second number is let us add the 457 with 634. So these are the concepts which are being taught in our school. The digits on the same placement carrying the same weight are going to add it. So we are not going to add 7 with 3 or 6. We're going to add 7 with 4 because they've carried the same weight, same placement. Similarly for the 5 and 3 and 4 and 6. Same concepts are being applied while adding the binary bits. So for the first addition, if 7 is being added with 4, what would be the result? Yes, that's 11. So 1 is the sum bit and the generated carry is being shifted to the higher place, which is going to be used in the next addition. So 5 will be added with 3 will be added with 1 to contribute the final result. So 5 plus 3 equals 8 and 8 plus 1 equals 9. Similarly, for the third placement, since no carry is being produced, 6 is being added with 4. So 6 plus 4 equals 10. 0 is the sum bit and 1 is the final carry. So these are the concepts that are as it is implemented on the binary data as well. So here we can see that at any placement there is a possibility that carry can be added. Either it's a decimal number or either it's a binary number or whatsoever the numbering system is. There is a chance that at any placement the carry that has been generated by the previous addition can also be added. So in a half adder circuit that do not possess that capability to add the carry in it. So we're going to switch to the full adder circuits. So a full adder circuit is basically a circuit that has the capability to produce the arithmetic sum of 3 bits. Let us discuss the example of the binary data. Let us assume that I'm gonna add 1 0 1 1 with 1 1 1. So for the first addition, 1 plus 1 equals 0 with 1 carry. Now for this addition, in which we're going to add 3 binary bits, half adder don't have any sort of capability to process those 3 binary bits. Here, in order to process these 3 binary bits, we require a full adder circuit that has the capability to add the 3 binary bits. So 1 plus 1 plus 1 equals 1 with 1 carry, and this process will be continued. So a full adder circuit is basically a circuit that has the capability to generate the arithmetic sum of 3 bits. So in order to add n bit binary numbers require the use of the full adder circuits, uh, and the process of addition process should be on a bit by bit basis, starting from least significant side till the most significant side. First of all, the least significant bits are added and the sum and carry are produced, and if the carry is produced, that is been switched to the next higher place, uh, then that carry is been added with the binary bits in order to produce the sum and carry result at that particular place. After the least significant bit addition at each position adds not only the respective bits of the word but must also consider a possible carry bit from addition at the previous position, which we have seen in this example. That carry can be produced or carry cannot be produced, but we have to deal all the possible cases in order to add those binary bits. So a full adder circuit is basically a circuit that has the 3 distinct input lines and has 2 outputs. One output is related to produce the summation result, and one, if any sort of carry has been produced, that is been indicated by that dedicated output. So now let us see the description of the full adder circuit and how these inputs S and C are related to, these outputs summation and carry are related to the inputs that are X, Y, and Z. This is table 4.4 of the book. And if we see that, for example, this combination in which 0 is being added with 1 and the resultant is being added with 1. So 0 plus 1 equals 1. The resultant 1 is then again added to 1. So 1 plus 1 equals 0 with 1 carry. So 0 plus 1 plus 1, this is basically equals to 2. So 1 0 is basically the resultant. So 0 is the value of sum and 1 is the value of carry. Similarly, for the last combination, that is this one, 1 added with 1 and again added with 1, the resultant is 3 basically. So sum bit is also 1 and carry bit is also 1. So if you see the simplification process, figure 4.6 represents the K-map for the full adder. For the sum, we cannot simplify because there is no pair that can be formed in this map, and in diagonal the pairing is not allowed. But for the carry, we can see that we've got three distinct pairs. This is the first pair, this is the second pair, and the third pair. And we are getting three terms: x and y, x and z, y and z. So and these terms are basically added in order to produce the sum of product terms. This is the logic diagram for the full adder that has been showed in figure 4.7. So these are the terms, the product terms that are being represented by these AND gates, and ultimately all these terms are being added or the ORed by using this OR gate in order to produce sum. Similarly, for the carry, these are the terms, three product terms that are being represented by these three AND gates, and the result of these three AND gates are ORed in order to produce the carry output. So these are the minimum number of resources that can be used to implement a full adder circuit. The important thing is that we can implement the circuits in the base form or the simplified form, or sometimes it's possible to convert those Boolean functions into their alternate forms. For example, if you see the expression for the sum, that is this one, the first term x and y prime and z prime, the second term x prime and y and z prime, the third term is x and y and z, and the fourth term is x prime and y prime and the z. These are the four main terms that are being extracted from the truth table. We can see that do possess an equivalent form if we apply some Boolean algebra and get something common that is between the terms. For example, from these first two terms we've taken z prime common, and similarly from these two terms we've taken z common. So this expression possesses the equivalent form, that is basically the z exclusive or x exclusive or y. So instead of implementing that with 4 AND gates and 1 OR gate, we can implement that with 2 exclusive OR gates. Similarly, for the carry output, this is the expression for the carry output, and that can have the equivalent form, that is z and x exclusive or y. X exclusive or y is already generated in the sum output. So this is the logic diagram if we implement those expressions, and we can see that we can easily implement a full adder circuit by using the half adders. If we have already got the half adders that are being implemented in the system, we can utilize those two half adders in order to implement the full adder. The first half adder, you can see this one. For the sum operation, x and y are applied to this exclusive OR gate. So x exclusive OR y is produced by this gate, and x and y is being produced by this gate. So the next exclusive or half adder setup, we're gonna use x exclusive OR y at its first input. You can see that the output of this gate is in fed directly to the input to this gate to the next exclusive OR gate of the next half adder, and the third input is basically the z, which is being fed to the second input of the second half adder circuit. So the sum operation is basically x exclusive OR y exclusive OR with third input, which is basically this z line. So this is the sum expression, and the carry expression is basically for the second half adder, that is x exclusive OR y and with the second input, which is basically connected with this z line. So the next thing is are going to use this additional OR gate in order to OR these two terms, which is x exclusive or y and z or x into y. So this is the carry expression that has been implemented, and this is the sum expression. So we can implement a full adder circuit by using the half adder circuits also. That is also the easy way to implement a full adder circuit. Now we have discussed the basic modules that are being used in the addition. If we have to add only the two binary bits, we can use half adders. If we have to add three binary bits, now then the half adder is not sufficient enough. We're gonna move to the full adder circuits. But what if the case we've got the two numbers that have the multiple binary bits? For example, let's assume we've got A and B are the two numbers, and we have to add A with B. So let us assume that A has a value 1, 0, 1. 1. My drawing is not so good because I'm drawing with a mouse. So and the B is 1, 1, 0, 1. If we add these two, so we're gonna add the bits that are on the same bit placement. So starting from the least significant side, 1 is being added with 1. These are the two binary bits. We can use half adder to add those two binary bits, or we can use the full adder with the third input that has been switched default to 0. So 1 plus 1 equals 0 with 1 carry. Now in this case, for the addition at this specific placement, we require a full adder. Half adder is not sufficient because we've got three binary bits here which we used to add. So 1 is being added with 1, and then the resultant is being added with 0. So 1 plus 1 equals 0 with 1 carry, and 0 plus 0 equals 0. The sum result is 0 and the carry result is 1. For the next addition, 1 is being added with 0 and 0 is being added with 1. So 1 plus 1 is basically 0 with 1 carry added with 0 equals 0, and the carry is moved to the next placement. For the next addition, we've got 1 plus 1 plus 1, that is basically 1 as a sum result and 1 as the final carry. So these are the sum bits, and this is the final carry. So here we can see that in order to add A and B, we require 4 full adders or 3 full adders and 1 half adder in order to add A and B correctly. So the binary adder is basically a digital circuit that produces the arithmetic sum of two binary numbers, not binary digits or bits. It can be constructed with full adders connected in cascade. We're going to see how we're going to connect those adders. The output carry from each full adder connected to the input carry to the next full adder in the chain. We can see this process from this example as well. The output carry generated in this addition is being fed to the next addition that has been connected to the input carry of the next full adder. So let us see another example in detail. So to demonstrate with a specific example, consider the two binary numbers. A is this and B is this. Both are the 4-bit numbers. So this is basically a 4-bit adder. We're going to implement that in this example. The sum that is being produced is 1, 1, 1, 0. And how this sum is being produced, we can see that these two numbers, this is A, this is B. AI and BI represents the bits basically. So this is A0, A1, A2 and A3, these 4 bits, and these 4 bits are B0, B1, B2 and B3. So if we're gonna and in the first case, the default carry is 0, because there is no need of a carry in order to add the two binary numbers in initial, unless and until there is some sort of previous addition that gonna forward those carry to the next addition. So A0 is being added with B0, so the sum result is 0 and the carry result is 1. which is being fed back for the next edition. Uh, we can say that feed forward to the next edition, uh, in which for the next edition, the next edition has been carried on. Sorry, the next edition has been carried out with the input carry which we've received B1 and A1. So 1 is been added with 1 and the resultant is been added with 1. So the sum bit is 0 and carry bit is 1, which is forwarded for the next edition. So this process is carried on. So let's see how we're going to implement that. So this is the block diagram for the 4-bit adders shown below. These are the 4 full adders which we're going to utilize in order to implement a 4-bit adder. Uh, A naught and B naught are applied at the first full adder. I can say that this is full adder 1, this is full adder number 2, this is full adder number 3, and this is full adder number 4. So the default carry is basically 0 for the first edition, and if we see the previous slide, the A0 and B0 are 1 1, this is 1, this is 1, this is again 1 A1, this is 1. Then A2 and B2 are 0 0, and A3 is 1 and B3 is 0. A3 is 1 and B3 is 0. For the first edition, 1 is being added with 1 and with default 0. The sum result is basically 0 and carry is forwarded for the next edition, and this process will continue. So these adders are basically connected in a cascaded orientation. So uh, we can say that the output of the carry output of one full adder is being applied to the carry input of the next high full adder. So these are the summation results that are being represented with S0, S1, S2 and S3, and C4 is basically the final carry that has been generated in this edition. So well student, this is all for the today's class. I hope so you've learned how to design the basic combinational logic modules. So let us summarize what we've discussed today in order to conclude our discussion. We've started our discussion by defining the combinational logic modules, and we've said that these are just the interconnection of the gates, and the important point was that these sorts of circuit don't possess any sort of memory element or the feedback element. Then we'll switch to the design principles, and we've studied the 4 design principles or the design methodology which we are going to opt in order to implement the combinational logical modules. First is to define the inputs and outputs. The second step was to define the relationship between the inputs and outputs in terms of the truth table. The third thing is the simplification if possible for the Boolean function, and the fourth thing is implementation and verification. Then we'll switch to the first design example, that was a code converter example, in which we've studied how a BCD code is being converted into access tree code. And afterward, we've discussed the basic adder modules that are being used for to perform the arithmetic operation, the addition arithmetic operation. So we've started with the 2-bit addition, that is for the half adder. Then we've switched to the 3-bit addition, that is with the full adder, and then we'll switch to the binary addition of the binary numbers of the multiple bits, in which A and B are the two binary numbers rather than the bits. And we've seen the setup that is the basic setup that is going to use in order to perform those addition. There are many alternative ways in order to implement those adders, and in future in the next classes we're going to discuss those modules also. So I hope so in today's class you've learned these modules, and I will be accepting your questions and any sort of queries in our online sessions for the question answers. And till now, Allah Hafiz and best of luck.